Hello. Yeah. Okay. Welcome to my talk. Let's get started. I'm going to tell you about classical simulation of peaked shallow quantum circuits. This is joint work with Sergey Bravi and David Gosset. It works. Okay. So in this talk, we consider n-qubit quantum circuits composed of 1 and 2 qubit gates. So when run on input the all-zero state, a circuit U specifies an n-qubit output state psi. Measuring psi in the computational basis induces an output distribution P over the set of all n-bit strings. Right? The probability of observing a string X is given by this expression. We're going to stick to these notations throughout the talk. We consider two classical simulation tasks. The first one is called sampling. So each time the circuit U is executed on a perfect quantum computer, right? Like here, the sample X is drawn from the distribution P. So for simulated sampling, the goal is to have a classical computer sampling from approximately the same distribution, hence matching the capability of a fault-tolerant quantum computer. So here approximately means up to inverse polynomial error in the TVD. For the second simulation task, the goal is to estimate the probability of observing a certain string X. So, approximately means up to inverse polynomial additive error. For this task, like suppose you have a classical simulation algorithm A that on input U can estimate the probability of observing all zeros. Then by feeding the circuit, right, like U dagger Z tensor and U as the input instead, for example, you can trick the algorithm to let you estimate other quantities like the magnitude of Pauli observables at the output of the circuit as well. Why do we care about the classical simulation of quantum circuits? Suppose we prove a theorem of the form. If a family of quantum circuits satisfies some property X, then that family of circuits can be efficiently classically simulated. Now, taking the logical contrapositive, we get a statement that says, if a family of quantum circuits demonstrate quantum advantage, then those circuits cannot satisfy the property X. Right? So classical simulation identifies necessary conditions for quantum advantage. Okay. There are three broad classically simulable quantum circuit families, each corresponding to a major framework or toolbox for classical simulation. Right? These are tensor network methods, the stabilizer formalism, and fermionic Gaussian states. And you'll hear more about fermionic Gaussian states in the next talk. There are many more specific properties X that can render circuits easy to simulate classically. For example, if the circuit depth is severely restricted to 2. Recently, there have been classical simulability results for specific families of random quantum circuits, like these two. In our work, we give classical simulation algorithms for peaked and shallow quantum circuits. I want to emphasize that our algorithms come about from a better understanding of the structure of peak shallow circuits. So what is a peaked shallow quantum circuit? We say a circuit U is shallow, right, if its circuit depth is a constant independent of the number of qubits. So here circuit depth is the number of layers of 1 and 2 qubit gates in the circuit. We say U is peaked if its maximum output probability is at least inverse polynomially large. Okay, and then peaked shallow means peaked and shallow. What's special about peaked quantum circuits? Suppose you run a circuit U on a perfect quantum computer polynomially many times to collect polynomially many samples, right? Then you would expect to see a collision, which means observing the same outcome string more than once if and only if the circuit U is peaked. Okay, and because of this collision property, Aronson has recently proposed peaked random circuit sampling for tackling the efficient verifiability issue of random circuit sampling experiments. So here the verification protocol roughly amounts to checking if you observe the peak among the set of strings you see. Okay. Yep. So that's for general peaked circuits. What about peaked shallow quantum circuits? I claim that the quantum part of many NISQ algorithms involves estimating the amplitudes of peaked shallow quantum circuits. Why? Because many NISQ algorithms, right, use a quantum computer to estimate the expected value of a tensor product observable at the output of a shallow circuit through Monte Carlo sampling, ideally to within inverse polynomial additive error. Okay, but first notice that if the magnitude of the value to be estimated, right, is much smaller than 1 over poly n, then the task is trivial because simply outputting 0 satisfies this inverse polynomial additive error accuracy requirement. However, if this value is at least 1 over poly n, then the circuit U dagger mu is peaked, according to our definition of peakness. Right, U dagger mu is still shallow because U is shallow, and the depth of U dagger mu is at most double the depth of U. So therefore, for this task, right, this task reduces to estimating the 0,0 amplitude of the shallow circuit U dagger mu, and it is non-trivial if and only if U dagger mu is peaked. Wait. Yeah, okay. So now I'm going to state our main results. We give classical sampling algorithms that do the following. Okay, on input an n-qubit shallow circuit U and an error tolerance epsilon that's at least 1 over poly n, our algorithms either output a string x drawn from some distribution p prime that's epsilon close to p in 1 norm, or throw a circuit is not peaked error. Okay. The runtimes of our algorithms depend on the geometric locality of the input circuit. For a 2D peak shallow circuit, we give a polynomial time algorithm. For a general unrestricted peak shallow circuit, we give a quasi-polynomial time algorithm. That's n to the O log n time. Okay, now what's in between polynomial and quasi-polynomial? For 3D and higher but constant spatial dimension, we give an almost polynomial time algorithm. In fact, n to the O log n time. Okay, this is for sampling, the first task. As a corollary, we obtain algorithms, classical simulation algorithms, for the second simulation task of output probability estimation. So an input, a shallow circuit U, a target string X, and an inverse polynomial epsilon. Our algorithms output a number P that approximates P of X to within epsilon additive error. Okay, it's important to note that for this task, we don't need to assume the input circuit U is peaked because the problem is trivial if it's not, and simply outputting 0 suffices. Okay, crucially, our algorithms know when to just output 0. Right, basically, it's when the sampling algorithms throw that circuit is not peaked error. Also recall that these algorithms can be used to estimate the magnitude of polyobservables, just like we discussed earlier. Okay, the time complexities of this output probability estimation algorithms are the same as the corresponding ones for sampling. So for the general architecture, our algorithm represents an exponential improvement in runtime over prior work. For 3D and higher, our algorithm has an exponentially smaller exponent. Right? Log n is exponentially smaller than poly log n. Yeah. So log of a million is like 5. Right. So it's pretty good. Okay. Okay. So this is our main results. So next, I'm going to describe how our general architecture algorithm works. Okay. It's quasi-polynomial time algorithm. Okay, so the key concept, okay, what are the key ideas, right? The light cone of an output qubit I is the set of all input qubits that are causally connected to the qubit I by the circuit. For example, here, the light cone of the second output qubit consists of the top 4 input qubits. Hello? Yeah, so the key property of light cones of shallow circuits is that if 2 output qubits I and J have disjoint light cones, then I and J have independent marginal output probabilities. So the joint marginal distribution of I and J is the product of the marginal for I and the marginal for J. Okay. So for a shallow depth D circuit where D is a constant, no matter how the gates are arranged, the expansion in the light cone size is at most 2 to the D, which is still just a constant. So from this, we can show that for a shallow circuit, any output qubit is correlated with only a constant number of other output qubits. In other words, this output distribution P has a limited dependency structure. Okay. So to gain some intuition about the output distribution of a peak shallow circuit, it is instructive to consider a toy model where P is a product distribution and the peak is the all-zero string. Firstly, we claim that for this toy model, the expected Hamming weight of a string x drawn from P is at most log n. And here's a one-line proof. I'll let you stare at the proof for a bit. Okay, it uses this cute AMGM inequality from high school math competition. Okay, so this shows that, right, we would expect to see at least n minus log n zeros, which means the expected Hamming weight, right, or the number of ones, is at most log n, right? So if n is a million, log a million is like 20, right? Okay. Right. Okay. Now it is straightforward to apply a multiplicative Chernoff bound to strengthen the expectation bound to a concentration bound, right? A high probability statement. Okay. It turns out that an analogous Hamming weight concentration property holds for the output distribution of peak shallow circuits. Okay. So we proved that for a peaked shallow circuit where each output bit is locally biased towards 0, its output distribution is concentrated on strings of Hamming weight at most log n. Right? The total probability mass occupied by higher Hamming weight strings is at most inverse polynomial. And this is the main structural theorem of peak shallow circuits that we prove. And we will see that it naturally leads to our classical simulation algorithm. Okay? But for comparison, it is known that the output distribution of a shallow, just shallow, but not necessarily peak circuit, is concentrated on a Hamming ball of radius square root of n. Okay. So log n Hamming weight concentration means what? It means like the output state psi mostly lives in this n to the log n dimensional low Hamming weight subspace. It's n to the log n dimensional because the total number of strings of Hamming weight at most log n is at most n to the log n. So we show that the output state of a peaked shallow circuit is well approximated by a state phi supported on the low Hamming weight subspace. The fidelity between phi and psi is at least 1 minus epsilon. And our algorithm constructs this state phi explicitly as follows. Okay, so we consider this Hamiltonian H, which is defined so that psi is the unique eigenstate of H corresponding to the largest eigenvalue 1. Every other eigenstate of H corresponds to a smaller eigenvalue. We consider the restriction of H onto the low Hamming weight subspace, which is just an n to the log n by n to the log n submatrix of H in the computational basis. We showed that the largest eigenvector of this much smaller matrix G is the approximation we want. Okay, so here's the algorithm. Okay, step 1. Construct G as a sparse matrix by computing all its non-zero matrix elements. All right. Then step 2, compute the largest eigenvalue of G with a corresponding eigenvector using some off-the-shelf eigenvalue eigensolver. Right? And then now stare at this largest eigenvalue, G, lambda 1 of G. Okay, if it's not close enough to 1, if it's like 0.8, right, then you throw the circuit is not peaked there. Okay, if it's 0.9999, right, then you return this eigenstate psi as the the state phi as the approximation to psi. Okay. Now, given access to this state phi as a big array of numbers, right, it should be clear how to do sampling and output probability estimation from here. Okay, this is how our general architecture algorithm works. It's pretty natural if you, given this Hamming weight concentration property. Okay. In the last part of the talk, I'm going to highlight the main ideas going into our polynomial time algorithm for 2D peak shallow circuits. It's a totally different algorithm. It's not just a different analysis. Okay, in a 2D quantum circuit, we have n qubits living on the vertices of a root n by root n grid. 2-qubit gates can only be applied to neighboring qubits, either like horizontally or vertically. Oh, right, like this. Hello? Okay, so the key property of shallow circuits we're going to exploit is again the notion of disjoint light cones. Okay, but for 2D shallow circuits, we can make the stronger statement that says if 2 qubits are sufficiently apart on the grid, like geometrically, then their light cones do not intersect. In this part, we're going to switch to mixed state, so we're going to let rho to denote the output state of the circuit U. Our strategy is to find a Hermitian matrix sigma such that the vector of its diagonal matrix elements is epsilon close to P. So here, diag of rho encodes P because it is the state. Diag of rho is the state obtained if you measure all qubits of rho in the computational basis. Erase all off-diagonal matrix elements. That's what you get if you measure in the computational basis. We also want the ability to compute every marginal of sigma efficiently, because it is known that having 1 and 2 imply we can approximately sample from P efficiently using this method by Bremner, Montanaro, and Shepard. 4 main ideas go into our 2D algorithm. So we apply the concepts of heavy slices and inclusion-exclusion introduced in prior work in a different way. In the end, we will construct a sigma that's a real linear combination of tensor products of matrix product states, okay, whose marginals can be organized into matrix vector products. That's for the second requirement, right? To compute the marginals. Okay. Okay, to begin, let's consider a root n by 2D plus 1 slice of qubits S. So here the width 2D plus 1 is precisely chosen so that the left and right regions have disjoint light cones. So if we trace out this S slice of qubits, we get a product state. All right, breaks entanglement, makes it easy to simulate, yeah. Okay, so we say like a width 2D plus 1 slice of qubits S is a heavy slice if the marginal probability of measuring all zeros on S is at least 0.99. Okay, for this definition to make sense, we assume for simplicity that the peak is the all zero string. Okay. We considered 2 operations that can be applied to a heavy slice. One is to measure all qubits in S. The other is to trace out all qubits in S and replace them with the all zero state. So it is not hard to show that measuring a heavy slice is well approximated by tracing it out and replacing it with all zeros in the sense of lemma 1. Right? This shouldn't be surprising if you stare at the definition of a heavy slice. Right? You're basically going to get 0 if you measure it, yeah. Okay. Wait. Okay, so for our first construction, let's consider partitioning the grid of qubits into alternating blue and red slices, each having width 2D plus 1. For a 2D peak shallow circuit, we show that all but log n of the red slices are heavy. So this is saying like heavy slices are everywhere. And this follows essentially from this log n Hemingway concentration property plus the 2D geometry. Okay, and the algorithm throws the circuit is not peaked there if it cannot find sufficiently many heavy slices. So now suppose our algorithm locates k heavy slices S1 through Sk. Right, what should we do with them? Like, is it a good idea to just trace them all out? Tracing out all heavy slices leaves the remaining system as a tensor product of polynomial-sized matrix product states, so we can compute its marginals efficiently. But because you lose 0.02, right, for each heavy slice traced out, the approximation error accumulates if you trace out more than 1. So tracing out all heavy slices achieves requirement 2, but not requirement 1. It turns out that if you compose lemma 1 differently like this, the error gets suppressed exponentially in the number of heavy slices in K. So now this is an interesting expression to look at. Wait. Okay, so expanding the product on the left-hand side, we get a term corresponding to measuring all heavy slices and the sum of terms with alternating signs. So this is what we mean by inclusion-exclusion. So each term in the sum, right, it traces out some heavy slices and measures the other ones. We give this complicated-looking expression a name. We call it A. So we see that A of rho is a sum of 2 to the k minus 1 terms, each tracing out at least 1 heavy slice. So lemma 3 implies that measuring all heavy slices is extremely well approximated by doing A. So does taking sigma to be A of rho work? Well, like we see that like the approximate, right? It's A of rho is overkilling the approximation accuracy requirement. But it is expensive to compute the marginals of A of rho because it is a sum of too many terms. It's like the problem is that the approximation is too good because we found too many heavy slices. So in the end, we combined the previous 2 approaches. Right? One was efficient but inaccurate, and the other one was too accurate but inefficient. We combined the 2 approaches to arrive at an algorithm that's both accurate and efficient. Okay, so this is what we actually do. Okay, we partition the grid of qubits into alternating blue and black regions, each having width log n. We show that using this heavy slices are everywhere argument, we can find L equal to log n heavy slices within each black region, even though the total width of a black region is only log n. Okay, we define AI to be the A operation applied to the ith black region, and finally we take sigma to be A1 through AT applied to rho. Okay, we show that measuring all heavy slices in all black regions is well approximated by sigma. So here, each mi corresponds to the channel that measures all heavy slices in the ith black region. So for L equal to log n, we plug into this expression, the approximation accuracy is good enough. Okay, and by construction, sigma is a real linear combination of tensor products of polynomial-sized matrix product states. Although each marginal of sigma is a sum of super polynomially many terms, we show that the sum can be organized into a matrix vector product and hence be computed efficiently. Okay. Okay. I'm going to end the talk here by leaving up some open problems. Thank you for your attention.
Yeah, please go ahead and ask questions. Just come up to the center of the room.
Hi, thanks for the great talk. Just a quick question. Could you comment about the quasi-polynomial dependence for the other architectures that you get? I guess in 2D you have a polynomial dependence, but could you comment about the other architectures? Why do you get a quasi?
For 3D and higher?
Yeah.
Right. So okay. So right. So how that part works is you apply this regional dissection construction on the last slide recursively to each dimension to shrink this, say in 3D, right? Shrink the size of the cube so log n by log n by log n cube, and then you do this recursively. And in the base case, you switch to the general architecture algorithm, okay? And then for this recursion, it's leaf dominated, so it's the base case taking the most time. And then for each base case, it takes log n to the log n time, and log n to the log n is n to the log n. That's how you get the almost polynomial time scaling.
Thank you.
Yeah.
Other questions?
So in the 2D case, you couldn't only do the square lattice, right? But also other planar graphs? And if yes, how does the polynomial scale on the degree of the graph?
I think our construction is sort of specific to a 2D grid. If your graph has higher degree, then it looks more like a 3D, 4D, 5D situation. But if it's more sparse, I think it's okay. If your connectivity graph is more sparse, it should be okay. If it's denser, then if it's like fully connected, then it's the all-to-all architecture, right? Yeah.
Thanks.
Yeah, go ahead.
Thanks for the great talk. So your theory can estimate the Born probabilities of given the binary string, right? So that the total of Born probability is very close to the probability in the TBD. But actually, from this, how we could to sample the binary string from this to obtain the distribution, then I think we should obtain the all probabilities of the probabilities of all binary strings. So how can we do that? Because the total binary string has many amounts of number. Right. For the general algorithm, right? We saw that the algorithm constructed this state phi as a big array of numbers. Right, its length is n to the log n. You store that big array of numbers into memory. Yes.
And this gives you the full distribution, right? Because you just set the probability of outcomes not in this low Hamming weight subspace to be 0. Okay, then you can just use this your favorite sampling method, knowing all of the probability entries.
Right. Okay.
Yeah. And for the 2D algorithm, we use that reduction by a Bremner, Montanaro, Shepard, right? Given the ability to compute marginals. Yeah. It's qubit by the robust qubit by qubit sampling.
Okay. Yeah. Thank you very much.
Yeah.
Okay, great. Let's thank Calvin again. Very nice talk.